Hi, in this video we're going to extend the work that we did on making a plot of the Sternberg task last week, and this time we're going to look at some specific models of the cognitive processing that occurs during the Sternberg task and see which of those models our data best supports. So let's get to it. You might recall that the Sternberg task is this basic procedure. The participant is given a list from 1 to 6 digits. These digits are called the memory set, and the participant's allowed to rehearse this list for a bit of time. I think in our task we used 2 seconds. After those 2 seconds have passed, the participant is then presented with a single digit. This number is called the probe, and the task for the participant is that they must indicate whether that probe digit is or is not a member of that memory set. Now, of course, what we did was we plotted response times, and if you recall from our previous work, we got a plot that looks something like this, okay, where response time looks to be increasing as a function of the number of symbols in that memory set. Now, let's just go back and see what that says about the type of cognitive processing that is occurring. So, the issue that we are trying to decide is an issue of serial versus parallel search. What does this mean? Well, if you search the one item at a time, okay, so through that memory set, if you, when you see the probe and you're searching, is this probe a member of the memory set, and you're just looking at each member one at a time, then it stands to reason that the more items there are to search, that is, the more items there are in that memory set, the longer it should take, since you're incrementing through them one at a time. And of course, the signature of that is that your RTs should increase as the memory set size increases. And if you recall, that's exactly what we're seeing right here. It looks like if you look at the RTs as a function of number of symbols in memory, it does seem to be increasing. On the other hand, if you can just look at all of the items at once, sort of in parallel, then it shouldn't matter how many there are. And in that case, the RTs will all be the same, regardless of the memory set size. So in that case, the signature would be a flat line. Our main question, though, is does RT increase with memory set size or not? So that question right there, if we answer that, we'll answer the question of serial versus parallel search. Now again, based on what we have seen so far with our data, it looks like, at least with the data that we presented in the last video, it looks like this is a serial search, because as you can see, there's this definite signature of the RTs increasing with set size. And so that seems to be a signature of serial processing. So if that search is serial, and by the way, this is exactly what Sternberg found, if that search is serial, then we can further investigate 2 other questions. We can also investigate whether that serial search is self-terminating or exhaustive. And the way we do this is by putting in the so-called negative probe trials. All right? These are the ones that the probe is not present in. Now, negative probe trials, they always require an exhaustive search, okay, because the target is not there, so the participant has to look through every one of the items in that memory set. But on the positive probe trials, the ones where the target actually is present, there's a couple of ways that we could process it. First is we could search through the set exhaustively. We could look at every single thing in the memory set. And if that's the case, then there'll be no difference between the positive probe trials and our negative probe trials. Okay? They'll have equal RTs. But on the positive probe trials, it might be the case, and this would be an efficient thing for us to do, that if we find that probe trial somewhere in the middle, then we would just stop the search right there. There's no need to go on all the way to the end. Once you have found that the probe is there, just stop, right? So in that case, that would be called a self-terminating search. Now you might think, this is surely the one that humans do, right? Because that would be the efficient thing to do. That would be the thing that surely we have evolved somehow to do this efficient procedure. It doesn't really make a lot of sense for us to search through the entire set even after we have found that probe, even after we have found that target. Well, what does the data say? Well, the data, it's not clear exactly yet what the data would look like. So let's look at just real quick some pictures of what our different predictions would look like. Now, as we mentioned earlier, the signature of parallel search would be a flat line on these RTs, which we've already seen that we don't have that. Because again, the idea is that we would be searching all things in memory in parallel, and so there would be no increase in RT as the set size increases. This, again, does not appear to be what we have. If you look back at our data that we have so far, we have this nice increasing line, so definitely not parallel. Now, if it is the case that it is serial, we can look at serial self-terminating or serial exhaustive. With serial self-terminating, so you've got the signature of RTs increasing with set size, but there should be a difference in the slopes of the target present versus target absent trials. Why is that? Well, if the target is present, the decision should be quicker. It should take less time. And so if the target is present, which is the open dot in this picture, then this slope, the RT per increment in set size should be less, right? Oh, in the end, it should take less RT than, if the target is present than if the target were absent. And so because the subject stops searching, you get a difference in slopes between the target present and target absent trials. Now, put that up aside the other possibility, which is serial exhaustive. In this case, you would get slopes of equal size or equal rate, because it doesn't matter whether the target is present or the target is absent. The participants continue to search every element in the list. And so the signature here basically is, first, decide if it's parallel or serial. Okay? And you do that by deciding, is it flat or is it increasing? Once it's increasing, you have to decide, is it serial self-terminating or is it serial exhaustive? And the signature, as you can see, is the slope of the line connecting the target present and target absent conditions. So essentially what we need to do is we need to start with our data. I'm going to go to RStudio now. We need to start with the data that we generated in our experiment and the plot that we got in our experiment last week. We need to start with this, but now we need to make separate lines connecting the black dots and the open dots. Okay? So if you will remember, the black dots were the target present trials and the open dots were the target absent trials. Okay. So here's what we're going to do. We're going to start assuming that you have made this plot. We're going to make some new plots, but you'll need the data that was generated to make that. And so the things in the environment here should look familiar. Specifically, you should have something called a P and an NP and something called set size. All right. And once we've got that, we can go from here. Okay, so here's what we're going to do first. First, we're going to construct this plot. I'm just going to make a little comment here to tell us what we're doing. We're going to do a plot to test the models of processing. Okay, so this is going to be a visual indicator of whether we have self-terminating architecture or exhaustive architecture. So the way we're going to do this is we're going to fit two separate regression lines. So last time, if you look at that plot that we did, we made one regression line through the means. Right? Well, this time we're going to make a regression line through the P's and the NP's separately. So here's how we would go about doing that. We're going to make two models. I'm going to call one model P, which will be the model for the probe present trials. And I'm going to do this as a linear model where P varies as a function of set size. Okay? So the syntax is very similar to what we did last week as well. P is the dependent variable and set size is the independent variable. And similarly, I'm going to make a model NP with the same syntax, LM of NP as a function of set size. Okay. So I'm going to execute both of these lines. I'm going to hit Control-Enter on line 3, Control-Enter on line 4. Now this doesn't do much, but if I want to see what these models look like, I can do a summary command, summary of model P. And let's blow this up completely where you can see this. So now remember, each of these summary commands gives us an estimate of the intercept and the slope. So when we look at just probe present trials, so this is the model P, we have an intercept of around 673 and a set size slope of around 30. So again, that's 30 milliseconds per increment. Now the question is the slope different when we do this for NP? So we'll find out real quickly here. We'll do a summary of model NP, and again, the main signature is the slope. Okay, so if we look at the slope here, it looks like it's about 24. Now you might say immediately, oh, they're different, right? This has got to be self-terminating architecture because the slopes are different, but not quite so fast. Remember, this is an estimation. This is an estimate of slope, and in that estimate is some error, some measurement error. We get that measurement error from our standard error column. So really what you can think about is with this summary, with this model P, the slope on the probe present, our estimate of slope is around 29.9 plus or minus the standard error, which is 6.2. Okay, so it could be anywhere from, well, let's go here, a little bit of space, 29.9 minus 6.2. Sorry, I can't type this morning. There's a low end of about 23.7 to 29.9 plus 6.2 to about 36.1. So our confidence interval on our slope is 23.7 to 36.1. Okay? So it's a wide range, right? Now the question is, what is our confidence interval on the NP? Well, for NP, the set size slope, the estimate was 24.1 plus or minus 3.7. 24.1 plus or minus 3.7, and so that gives us a confidence interval of, let's go back to our R console, 24.1 minus 3.7, which is about 20.4 to 24.1 plus 3.7, which is about 27.8. 20.4 up to 27.8. Now, these certainly look different, but they overlap quite a bit. So one might be a little curious here, are these really different slopes or not? Well, at the end, we're going to test this definitively, but right now, it kind of looks like these might not be the same. These might be the same slope, right? They might not be different after all. And remember, if they are not different, if they are the same slope, that is actually evidence for serial exhaustive architecture. It's a very strange way for humans to do it, but that seems to be the case. Okay? Now that's doing it with just the linear models, but it'd also be very helpful to make plots of the probe present and not present trials separately. So that's what we're going to do now. This is a plot that Sternberg did not include in his original paper, but I think it'd be a nice touch for our manuscript. So here's how we do it. We've got everything that we need already in our environment. We should be able to just do this. We're going to do a plot command. Okay. X will be set size, just like last time. But this time, instead of applying the means, we're going to do y equals p. These are just going to be the probe trials, the probe present trials themselves. Now we're going to make things a little nicer here. We're going to use a PCH of 19. That's that solid dot. We'll use the same XLab as before. So I think it was number of symbols in memory, something like that. Whatever you used last time will be fine for this. YLab will still be RT in milliseconds. One thing I'm going to do a little bit different than the last video is I'm going to put an XLem, and I'm going to put C from 0 to 6, and I'll show you why in just a second. And then the YLem, I'm going to use 650 to 900. You can just use the one we did last time too. I don't remember if that was exactly it or not. This should do it for us. Let's execute the plot. We'll execute line 8 here. Okay. All right. This gives us a pretty nice plot. All right. Now, one thing that we can do now is we can fit the regression model through this. Remember, this is kind of strange. The way this data looks, these are all in a nice line. For some reason, that one that's at 3 is kind of kicked off there. But for the most part, this is a pretty good fit. But we can stick the regression line in by just saying AB line of model P. Okay. So that looks pretty nice. That looks pretty nice. Okay, now we're going to do the exact same thing for the NPs. We're going to put the NPs in as open dots and put a dashed line through them. Again, the reason we're putting the lines through is because it's these lines that are the signature of the processing. If the lines have the same slope, then we have evidence for serial exhaustive architecture. If they're different slopes, then we have evidence for serial self-terminating. Now, the way we can get the extra points in there is use a points command. So if we drew a new plot, it would override our current plot. We don't want to do that. So let's just do points. X is the set size. Y is in P. And we'll use a different PCH. We'll use PCH equals 1. That'll give us an open dot. And that's all we need. We've already defined all the other plot parameters. So we'll just add these points in. Let's execute line 16. And there's our probe not present trials. And let's fit the line through there. We'll do AB line model NP. But we need, if we do that, it's going to give us another solid line. But I'd like a dashed line. So the way we do this is after we put in model NP, we put in an LTY. LTY is line type. And we'll just set line type equal to 2. Line type equal 2 gives us a nice dashed line. Let's execute line 18, see what we get. So there's what we get. We get a dashed line that doesn't look exactly parallel to the solid line, but it does look similar. It's certainly not the picture. Remember the signature picture from our presentation. That's what it should look like if it's serial self-terminating. And it should be in that order, too. The target present should be the lower slope line. The target absence should take longer. That's not what's happening here at all. So this seems to be pretty good evidence for our serial exhaustive architecture. It's just so strange. Okay. By the way, you might be wondering, why did I put this little xlim equals 0 to 6? Well, here's why. Remember last time when we do the summary of, let's just pick one, model P. Okay, let me blow this down just a little bit so that you can see the estimates. Remember last time in the video, I had a little bit of an issue with the intercept not matching up with what I thought the intercept should be. That's because the way we did the plot did not give us a true y-intercept. To have a true y-intercept, you have to have x equals 0 visible in the graph. And in our graph before, the y-axis was about right here. And so that's not where the y-intercept is. But now it looks like it all works out pretty well. This intercept is around 672, which, as you can see, is about right there. Okay, so just a little bit less than halfway in between 650 and 700. That's about right. Same thing with the model NP. If we do a summary on that, that intercept should match up as well. So that intercept is about 725, looks like about where we are. So now you can see that the intercepts actually do match up with what our regression models do fit them. Okay. One last thing I'd like to do to this plot, there's a lot of stuff floating around up here. Which one's P, which one's NP? We don't have a legend, right? So let's make a legend that actually tells us all this. So we do that with the legend command. First argument of the legend command is to tell it where to go, right? Where are the x and y coordinates of where to actually put the legend. And I'm going to put them at x equals 3, so I'm going to put its left edge about right here. And then y equals, I played around with this before, I think 720 is a pretty good place. All right. Now, what does the legend actually say? Well, we say that by saying legend equals, and we're going to have two things. We're going to have target present. We'll put that in quotes. And then the second one is target not present. Just like that. Now, in that order, we then tell it what the PCHs are. So the PCHs are 19 and 1, respectively. Why not 119? Well, it all depends on what the first element of your legend is. Since the first element is target present, we want the PCH code, the solid dot that goes along with that, and that's PCH 19. And then the second element in our legend is target not present. We want the PCH of 1. And then same thing with line type, LTY, and that's going to be C from, let's see, 1 and 2. The first one we didn't even put an LTY. That's by default a solid line. It's LTY1, but then this dash line is LTY2. And that should be enough. Let's execute line 20, see what we get. We got a pretty nice little legend there. Okay, now we can clearly see both the dot and the line type indicating which one is the target present trials and which one is the target not present trials. So now you have a pretty nice graph that you can export and put into your manuscript when that time comes. Okay, so the last thing we're going to do is we're going to now definitively test the hypothesis that these two slopes are the same, right? Is this truly evidence for serial exhaustive processing? Okay. So I'm going to put a little comment to say what we're doing here. We're going to test whether slope of P equals slope of NP. And the way we're going to do this is similar to how one does a paired samples t-test. We're not actually going to do a hypothesis test with it per se. We're going to use sort of an inference procedure based on our regression model. But what we're going to do is we're going to build a regression model on the differences between P and NP. Okay? The reasoning for that is fairly simple. If the differences between these, on average, don't change, then that tells you that the slopes are the same. And if the differences don't change, that means that the differences will have a slope of 0. Okay? So work through that logic again. It's whether the differences change. If the differences between these pairs of dots don't change, and as you can see here, at least once you start from 2 on, the vertical differences are fairly consistent. If those differences don't change, then that means that the slopes originally are the same. So here's what we can do. We can say model comp for comparison or whatever. You can call it whatever you want. I'm going to call it model comp. I'm going to build an LM on P minus NP. Okay? P minus NP is a way to express the differences between the P's and NP's. And I'm going to let that vary as a function of set size. And I want to test the slopes on that. So there's the model. Let's do a summary. Summary of model comp. And here's what we get. In this case, it doesn't really matter what the intercept is. That's not the important part. The important part is the estimate of the slope. Okay? So the estimate of the slope on this model, the estimate is let's call it 5.9 plus or minus, and look at the standard error. The standard error is 8.1. All right? So what does this give us as a confidence interval? This gives us 5.9 minus 8.1, which is negative 2.2, and 5.9 plus 8.1, which is plus 14. So our 95% confidence interval, or sorry, it's not a 95% confidence interval, that would be even bigger. This is more of a 68% confidence interval. But our confidence interval on the slope is negative 2.2 to 14. What that means is that we're reasonably confident that that slope is 0. All right? 0 is contained in this interval. And since 0 is contained in that interval, then we're reasonably confident that the slopes coming from P and NP are the same. They are equal to each other. And so this is a way that we would, by an inferential procedure, decide whether the slopes are the same or different. So at least on the data that we presented in this video and that we started with in the last video, it appears that our participants are exhaustively searching the entire memory set regardless of whether the target is present or the target is absent. What an inefficient thing to do. And of course, the end of the story is if you've read the Sternberg paper, you realize that Sternberg found exactly this as well. And in fact, if you look in the Sternberg paper, you can find where he does this procedure. He doesn't, it's kind of hidden, but I challenge you to go through there and find that. So that's the analyses for the Sternberg project. We're now ready to probably write up the manuscript, and this should give you all of the technical things that you need in order to do that. So until next time, I will see you. Let me know if you have any questions, and then we'll see you next time.